This is my large RGB LED wall with 768 pixels. It can display animations, images, some patterns, and other random stuff. All this runs on an Arduino with over 60 frames and can even run on an ATtiny 84. Originally I'd planned for ping pong balls to be used as diffusers, but I didn't have time to glue them on, so I'll leave that to a later video. Let's start at the beginning. The project first started with BitLooney's own RGB ping pong LED wall video. I was really inspired by this that I decided to make my own version of it for this ISP, and here I will take you through my journey. I first started with figuring out how to control the SK6812 RGBW neopixels I plan to use on my matrix, which are like regular RGB neopixels in that they use a one-wire protocol to write an 8-bit brightness value of red, green, and blue LEDs. But these RGBW LEDs includes an extra white LED to save power and produce a purer white, which means that an extra byte is needed to control it. Since the popular fast LED library did not support RGBW LEDs, I coded a sketch to control them by toggling pins on the AVR microcontrollers with nanosecond timing, as the one-wire protocol calls for, using the low-level port manipulation concepts recently learned in class. This involved carefully calculating the number of clock cycles of each instruction written to adhere to the precise timings of sending bits. Every clock cycle counts, so global interrupts must be disabled when pushing the data out to avoid unwanted flickering. Afterwards, I began creating a matrix design that's modular and relatively simple and cheap for a large RGBW wall. It's similar to BitLooney's own wall, but uses thin strips of 8 LEDs and connectors for each strip instead, which allows for a variety of matrix sizes to be created. The size of the strips also saves money on PCB shipping and manufacturing costs as opposed to large matrix panels. I then began work on the design, where each board needed huge traces and ground planes for the amount of current these LEDs consume. Male headers with jumper connectors on the PCBs allow for routing of the data signals to other LED strips for modular control, and the strips were designed symmetrically, so that rotating it allows data to flow left or right with power and ground in the same position. All these features allow many different ways of sending data to the wall. Here it is configured in a snake pattern with one serial data output. Plugging in 7 other data outputs and rearranging the wall allows for an 8-way parallel zigzag output. While designing those PCBs, I also created smaller ones as a complement to the large wall, which also employs the same principles of modular design and data routing. They include a bottom connector board and a top LED strip. Since I needed a lot of PCBs, I panelized the connectors and small LED strips to reduce the cost and ordered them using JLC PCBs without their assembly service. Even so, the prices were still pretty hefty, so I made sure my PCB designs were absolutely correct as there was no ordering a second time. I also bought a huge roll of LEDs and other external components. While waiting for them to arrive, I continued with software. Here I figured out that all the pins on a port can be toggled in one command, allowing for parallel writing of bits instead of serial writing, therefore increasing the frame rate of the matrix. As you can see, a low-level write to a port only takes 2 clock cycles, therefore the 8 pins can be controlled in parallel on this one line. If you want to use other pins on the port, you have to include some bit math to only toggle the pins used for the LEDs, which take an extra 2 clock cycles. Also, the delays could be taken out to instead control other ports, therefore allowing 16 or 24 parallel control, making good use of an Arduino Mega's pins, but 8-way parallel control was good enough for me. To send out data, I created a 2D byte array buffer with each column representing the color bit and each row representing a pixel. Each 8-bit value is then sequentially sent out to the port to generate the required colors. To change a pixel, a custom function converts the RGB values to corresponding values in this array. This buffer only works with the 8-way parallel zigzag configuration. Meanwhile, I also experimented with the AVR timers and interrupt service routines, but in the end opted with delays as the ISRs did not execute fast enough. After a week, the PCBs arrived and I was very pleased with the paneling as it was my first time panelizing PCBs. At this time I was still playing around with the software, though I did immediately solder up a few strips and connectors and was happy to see everything working well. So I continued with software and left construction and soldering till later. This was not the best idea. A few weeks later, I finally worked on constructing the wall, where I first designed the structural support to mount the connectors and LED strips. I had initially planned to create it out of wooden sheets for a proper mounting surface, but instead opted for a minimalist wooden skeleton frame made out of thin boards, which would be lighter, easier, and way cheaper to construct, though unfortunately the power supply cannot be mounted to the wall, although one could probably add on some more wood panels to do so. And with that, I got the materials ready. With some help, I began measuring and building the frame using some soldered strips and connector boards as guides. It took quite a while to get everything right. Next was the soldering. This only started a week and a half before the deadline, since for some reason I thought that soldering 768 LEDs and 128 connectors wouldn't take long. Soldering the first components, I soon realized my grave misconception. It took 4 hours just to solder a third of the LED strips, and another 4 for the third of the connectors. I was not very happy. In hindsight, I should have spread out the soldering over the weeks and left the software improvements till later. This is why you don't procrastinate. If I were to do this again, I'd use a hot air station or get them assembled by a PCB manufacturer. After soldering, I still couldn't rest, as I then had to mount each connector to the frame, wire it up, and route the data signals. One third done. Eventually, I had only completed the top third of the wall, and, when powering it on, many of the strips didn't, due to sloppy and rushed soldering. I removed these strips and resoldered the joints. I had to repeat this quite a few times to eventually get the strips to behave properly. But once done, I was quite satisfied, albeit very tired. I also managed to program a few effects as something to show for my upcoming school presentation. After that, it was time to repeat the process 2 more times. But to make sure I was soldering the LEDs correctly, I mounted some connector boards, put male headers in, and soldered the strip directly on where I tested each of the color components with some test patterns. To solder the LEDs, I solder one pad, put the LED on with my fingers, and reflow the solder onto it to hold it in place, where I then solder the rest of the pads. This only needs to be repeated 512 more times. Along the way there were some soldering issues. For example, I would frequently put too much solder on where it would overlap a small metal piece, keeping the white component on. Reflowing and removing some of the solder fixed it. When soldering and testing the remaining strips, I also managed to solder a short on one of the capacitor pads, which was easily removed, and luckily, the LEDs were fine.
There we go.
Sometimes I even forgot to solder some pads. Anyway, done the LEDs, now the connectors. For these boards, I got these long 40-pin female headers for cheap, where I split them into groups of 3. There were a lot of pins pulled out and quite a bit of cutting. In total, the soldering spanned several days and many hours, and in the end, I didn't even have time to solder the supporting capacitors for the LEDs.
Oh, I am done. All this.
768 LEDs and 120 connectors are not to be underestimated. Now it was mounting, wiring, and configuring time. Here I configure the wall in an 8-way parallel zigzag pattern. And finally, it was done. Let's test it. And it worked wonderfully, though I did forget to
Oh.
plug in the jumpers for a few connectors. Afterward, I designed a case for the smaller LED strips with a grid and a diffuser panel. They fit perfectly, though the diffuser was a tad too thin. Next time I'll print it a bit thicker, but it still looks great and complements the wall well. With the time I had left, I created some 32 by 24 images through pixel art or downscaling, and programmed an image converter on processing to convert these images into the 2D LED buffer arrays, where I can copy and paste it from a text file into the sketch. To store it, I needed to use program memory, as SRAM exceeded capacity to hold its size, which required some special functions to properly read the data stored in program memory. The result impressed me a lot. However, each frame takes up a whopping 3072 bytes of memory. One way to reduce this memory footprint is to calculate and send out color bits on the fly, but this limits the display to patterns generated with for loops. This is how I created the rainbow pattern. Also, the output is serial only, as parallel port bit banging does not work with this method. The extra math required takes too long for the LEDs to accept. So the best thing would be to use a larger memory board like the Arduino Mega or read from an SD card. Once I was done programming and confirmed that all the LEDs were working, I glued on some ping pong balls which should hopefully not ruin the LEDs. To see if anything went wrong, I tested each strip after gluing. Although it looked great, it was unfortunately taking quite a while to glue them on, and my first few strips were a bit messy, so I left gluing the ping pong balls to another day when I have more time. So, with tons of planning, coding, manual labor, and a few lessons learned about time management, I created my own RGB LED wall, which can run off any Arduino and even an ATtiny84 with use of parallel port manipulation. As you can see, I've hooked up the ATtiny84 to the wall, and it is working flawlessly. I am still really impressed that such a small chip can control such a large amount of LEDs. In the future, I would like to program some other features such as message scrolling, custom color palettes, and gamma correction. Here you can see that I tried hooking up a wall to the ESP32 cam, but I was only able to get limited functionality. Luckily, all of this is in software, and I'll definitely sort it out in the future, and hopefully make a video on the additional features. Still, I have to say that I'm very happy with what I have achieved so far. The cost and labor was certainly worth it, and I hope that you too, like me, enjoy the outcome. I'll definitely get the ping pong balls glued on to show in a later video, and hopefully I can get it mounted somewhere and improve on it further, but that will all have to wait for another time. Thank you for watching.